Okay, thank you, Michele. Thank you for the invitation. Thank you for giving us this opportunity to present our paper, and thank you all for people that stay with us today and to the discussion that read the paper and make comments on our work. Since we are three authors, we will split the presentation in two parts, and then Rebecca will lead the rejoinder. That's the title of the paper, and the main topic, as you know, is record linkage. Record linkage is it's a class of algorithmic techniques that try to bring together information from different records, from different statistical information, and because you believe that those records may belong to the same person, to the same unit. And of course, linkage is a statistical step, and is based on what you observe on those strings, on the variables that you use for matching. Of course, if two records agree or disagree on all matching variable, we are pretty sure that they correspond or they do not correspond to the same person. But in practice, it never happens. We have some intermediate situation, and then we need to make a decision in a way or another if that pair of records are a true match or not. And of course, this task would be very easy if we have an entity identifier. But this identifier is often not available, so we should make inference on and assign a probability to the event that two records belong to the same person or not. There are many challenges in this data linkage problem. Some of these challenges are common to any statistical problem, like errors in measurement error, variation of the data, or some missing data in your data set. But some other challenges are very specific of record linkage, because, for example, when you compare different data sets, you may have you may experience the fact that data on the same variable, on the same phenomenon, are recorded and maintained in a different way. For example, we will see an example with different version in which the date of birth can be registered, and also data coming from the same person can change over time. One person can be married and then divorced and things like that. And then there are some other typical problems which arise in when the key variable that you are using are strings. Then you have misspelling, transposition. You can split words and put words together in a fusion, and many other difficulties that makes this problem quite challenging. These are examples that I took from the web. There's no explanation needed. There are people with the same name. Maybe both of them are famous, and it may be difficult for an algorithm to distinguish which record belongs to. This is an example of misspelling. I'm sure that if you read that school in the street, you're probably not. You have no doubt that there is a school there, but things like that can happen. Why do we need to do data integration? For many different reasons. Probably the most important reason is that we want to make some data analysis that would be impossible to do with one single separate file. That's what we call post-linkage inference. You want to calibrate a statistical model, and for that statistical model, you need to collect information from different files. you integrate data because you want to improve your data quality, or maybe you want to simply maintain a master data register, and you want to enrich this data register with some other information coming from maybe from some administrative list. And of course, this is what we would like to have, but there are many problems in doing that, as I already mentioned. And two big problems that I didn't mention yet is the course of dimensionality. If you want to merge two data file, and in real application, those data files are huge, and then making comparison for each single pair may be prohibitive from a computational perspective. And then there are a lot of problems, a lot of privacy problem, and this is another fascinating issue that I will not touch today, which is which goes under the name of privacy preserving record linkage, but I won't talk about it. Okay, let me translate the last slide in statistical terms. And we do record linkage for complementary reason. One is to make record linkage just per se, to obtain a larger of reference data set, as I already said. Or on a different ground, you may want to make record linkage because you want to do a statistical analysis after the linkage step. These two goals may require different strategies from the statistician, because there may be a feedback effect in the two steps analysis, and so results in using the first perspective or the second perspective may be different. And Andrea at the end will show you an example of it. I will focus on both those aspects, and so I will try to tell you what are our contribution to the Bayesian record linkage and how to use the linked data for estimating the size of a population. And an example that we will consider is what happened in Syria recently, and we have two lists of recorded victims that were killed in that conflict, and their name are collected in these two databases. I will not link here because I share only this screen, but I can give you the website address. And both this data set include the variable that I will list below: the first name, the family name, the date of death, and where the death took place, in which place of Syria. And consider that this example is not so easy, because in many casualties, it happened that an entire family were killed by a bomb, and so probably many different units with the same last name are present in both the registers. So let's try now to formalize a little bit what we did. Our model takes much of the wind from the original paper by Rebecca, Steve Feinberg, and Hall, a JASA paper of 2016. We assume that we have L different databases, L list, and we assume that our population consists of an unknown number of individuals, let's say capital M. What we see is a vector Vij, which consists of P different key variables, the variable which are present in all of the L list, and Vij is a record related to the record J in file I. Of course, in file I, there will be ni different records, and n is the total sample size, let's say sample size. What we do not observe is j prime tilde. Now j prime ranges from 1 to n because it's related to the latent individual, and v tilde is the true vector of variable observed on that individual. Finally, lambda ij is indicates a number. Also, the lambdas range between 1 to n, and they denote which individual correspond the value Vij. So lambda ij is a strange mathematical object because it's not a matrix, because each single file has a different size, and it represents our parameter of interest in a sense in a record linkage application. Of course, we allow both duplication on the same list, and it happens when lambda, there are two lambda which are equal, and the I is the same file. On the other hand, when both the file index and the record index are different, this is just a match between two records into different lists. What are the model assumptions that we made? We assume that all the v tilde vectors, the one related to the v tilde random variable related to the various individual and concerning the variable L are independently drawn from that distribution with a given number of different possible value and related probabilities. So we have, let's say, a non-parametric distribution over a discrete number of possible values, and then assume that those observations are independent. The covariance values are independent of each other. So the distribution of the latent vector or the latent matrix is given by the product over all the individuals and the product over the different covariates, and can be written this way. On the other hand, this is what we do not see. What we see is modeled through the hit and miss model. So we assume that what we observe, Vijl, is the observation on variable L, record J, file I, and this is a simple mixture, a mixture between a Dirac delta, so with probability 1 minus alpha, we observe the correct value, and with probability alpha, we observe another possible covariate value of that particular key variable. So this is the model comes from a famous paper by Kopas and Hilton, 1990. Then we assume, as we already said, a conditional independence among all the covariants, also in the observational process. So our, let's say, likelihood function is the probability of the observed V given V tilde, given all the parameters that I already introduced. Alpha, remember that alpha is the parameter which describe the error mechanism in our data. And alpha has two different parameters, two different indexes. One is related to which individual is connected to, and L is the variable. So it's a product over the three different quantities, I, J, and L. So in a Bayesian framework, of course, we need to discuss prior distribution. And what we assume for lambda, so now I discussed the prior conditional on a given population size n. So given n, given a population size, the prior distribution over lambdas is uniform. It's uniform over this label space. So we assume that each single individual can choose its own label with probability 1 over n, because there are no other information about that we can use at this step. This is the same as assuming that we have L independent simple random sampling with replacement. Each random sampling has size nj, the size of our data set. Of course, a prior distribution which is uniform on the label space does not imply a uniform prior over the partition space, because there are several different relabeling of the same partition. So for example, just to make things clear, consider the case in which you have just one list. The population size is very small, it's 5, and you observe 4 records. If the true labels are 3, 5, 2, 5, it means that we observe the individual 3 once, the individual 5 twice, individual 2 once. Another way of representing this vector lambda is to tell you what is the partition of the sample, and the partition can be written just like 1, 2, 4, and 3, where 1 corresponds to the first individual, 2 and 4 means the second and the fourth record, and 3 the last one. And of course, to make a one-to-one comparison between lambda and z, you have to complement z with u. U is the choice of the labels that you attach to that partition. Of course, there are many other labels u that correspond to the same partition. So, sorry about that. So, moving from lambda to z and u, I can reread the prior distribution of lambda over a prior distribution for z and u. And you even still conditioning on n, the distribution of z given n is the previous distribution over lambda times the number of relabeling that you can consider for the same partition. And of course, the distribution of u given z can be obtained as a ratio of the previous two. Sorry, I did not introduce k. K is the number of the blocks in that given partition. So if we denote k as the number of blocks in a partition, which correspond in a record linkage literature is the number of different units that you are dealing with, then the given k, the prior distribution over the partition is uniform. But the distribution on k is not uniform at all, because it consider is a combinatoric formula which include the Stirling number of the second time, that is the number of ways in which you can partition n balls into k groups, let's say, and all those factorial. So all this analysis is made given n, and then we need a prior on n, and so we assume a proper prior, so n minus power minus g with g less than 1. In our opinion, an interesting aspect of this prior is that it can be reconstructed using a different approach. So now let's clean your mind and imagine a different situation in which each single unit in the population, uj prime, j prime is the index ranging from 1 to n, imagine that each single unit is exposed to be captured a random number of times. So there are tj prime occasion in which the unit j prime can be captured in the list j, okay, because we want to allow for duplication. Now, if tj prime is Poisson, and then if each of these try is a success with probability pj, so it's a Bernoulli random variable, then the number of times that that individual is captured, is present in the list J is Poisson with parameter Pj times delta J. And also Nj is the sum of all the those Poisson distribution over the n individuals. And so Nj will be Poisson with parameter psi j times n, which is the number of Poisson that we are summing. So another way of obtaining the previous prior is to simply assuming a uniform prior conditional on the sample sizes. So if we fix the sample size N1 and L, where L is the number of least, then we obtain the same prior using this different construction. It may be interesting to notice that this different construction opens the way to different modelization, because if we change some of these assumptions on Poisson, Bernoulli, and so on, we may have different prior on the level space, justified by a different construction of our model. Now let's go back to the likelihood function, and if we know lambda, so we know z and u, then conditioning on z and u, we may notice, it can be proved, but it's very easy to notice that the distribution over distribution of the observed quantity v can be factorized in a product over the different blocks of the partition, because in each block there is a single unit, a single entity. The same is true for PV tilde, because V tilde is the vector of the true values. And again, it can be written, the joint density can be written as a product over the blocks of the partition. Then after integrating out V tilde, so we are able to get rid of the latent true value of the variable, of the true records. We have a conditional distribution of the observed value given z and u, or lambda, and given the other parameters. N is a sample size, alpha is the error probabilities, is the measurement error probabilities, and thetas are the probabilities on the population, at the population level of the covariates. So the final likelihood, just skipping some detail, the final likelihood conditional on z and u, but after integrating out the v tilde values, is a simple product over the blocks and over the variable. So the mixture structure disappear in a sense, because we have integrated out with in the previous slide. We miss to describe the prior over the measurement error parameter alpha. We re-parameterize in terms of the logit of each single alpha. We call it beta. So beta is the logit of alpha. And we put a series of independent and identically distributed normal prior with parameter psi and tau squared over all the betas. There is, you see, there is a beta for each L and for each J prime for each unit, and all these betas have the same distribution, and the hyperparameter psi as an hyperprior with mean, which is a value that you should give in exogenous way to the model. So this is a very important parameter. It says how precise is your measurement process, in a sense. In the application that we will show in a moment, we have an alpha tilde parameter which is set at 0.01, and S square is the hypervariance, which is 0.1, and chi-square is 0.5. But let me just say that, I mean, I spent many years in objective base, but this is not an example in which you can be objective in a sense, because the model is so huge, is so over parameterized in a sense that you need to insert some prior information on the way in which data were collected in a sense. A minor impact is from theta. So you may assume a Dirichlet prior over the simplex of the parameter theta for each single covariate, and we always use a uniform prior. From the computational perspective, we didn't do any fancy. We used just a metropolis within Gibbs algorithm, and then Andrea will introduce to the algorithm and the example. I'm not able to see whether there are some questions. Michele, can you help me?
Yes, not at the moment.
Okay, good.
Yes, not at the moment, I think. Unless, let's see if there is any question for clarification, we may accept them now quickly. You may also raise your hand.
You can stop us whenever you want.
Okay, let's see.
Thanks.
Perfect. So let's have Andrea. Perfect.
Okay, thanks Brunero for the talk so far. I want also to thank Michele for the organization of the webinar, and also thanks to the discussant. And I will describe now the application that we did with the model that we have presented. And I start with a benchmark example in the record linkage community, which is the RL500 dataset. This is a small dataset with only 500 synthetic records. This dataset represents a set of German names, and in particular, here are reported the complete names and the date of birth. Inside these 500 records, 50 records represent duplications, and so are duplicated and distorted version of other records already presented inside the dataset. So in this case, in this first case, we are in a single list framework with 450 entities observed at the sample size. And here you can look at the first part of the dataset. Okay, in order to apply our model, we need to transform the name and the surname because, as Brunero explained, we use categorical variables. And in particular, we apply the SoundX algorithm to do this. And the SoundX code for a name consists of a letter followed by 3 numerical digits. And the letter, of course, is the first letter of the name or of the surname. And the digits encode the remaining consonants. For example, consonants at similar place of articulation share the same digit. So, for example, the labials, B, F, P, and V, are encoded with the same number, which is 1. So this is a trick to avoid to use the string, the strings, basically. Note also that in this application, we also transform the here birth into 4 fields. So we end up with 14 key variables. Okay, let's start to look better at the prior modeling. In particular, we use a prior for n, which is 1 over n to g, where g is equal to a singular value, which is 1.02, because this value is such that the prior expectation on k, the number of different entities, is exactly 450. Anyway, I want to anticipate that this choice, the choice of G, is not influential like other choice that we did in the prior modeling. As Brunero said, we take a uniform on the simplex for the probabilities of the different categories of the key variables, and for the parameter representing the error probabilities, we use a quite strong assumption, because as Brunero said, we use a prior such that the expected value for alpha j prime L is the error probability that we can have for a population entity J prime in the field L. This prior expectation is 0.01, and the 0.99 quantile is very small because is equal to 0.06. So we are quite informative in this choice, but we believe, and we think that this is an important point, that such kind of prior modeling can be also used in other deduplication frameworks. This is because low values of alpha j prime basically will force cluster to have a reduced within cluster variability. That's because we are saying that we expect very similar duplications. And of course, since the clusters are formed by these duplications, we reduce in this way, well, the expected size of this cluster, which is an important aspect for the, well, to obtain the microcluster. So in some sense, what Brunero was saying before, that we cannot do an objective or a non-informative analysis, but can be also, we can also say that this kind of prior modeling is yeah, in some sense typical, is a representative for the duplications setting. And the importance of the measurement errors has been noted also in a recent Biometrica paper by John Drovblum and Danson, and where they say that entity resolution via microcluster identifications requires that the measurement error go to zero as the number of entities increase. So they theoretically say that we need a very small measurement error for the microcluster being effective. So we just adding in this context the fact that okay, we can obtain entity resolution via microcluster also with this prior, with an informative prior on the parameters. Okay, let's give a look to the posterior. Here in this figure, in the first panel on the left, you can see the posterior on K and also the prior. So even if our choice of G was particular, you can see the red line, which is the prior that we are putting for the number of different entities. This is very flat in where the posterior concentrates. So we are able to, well, to propagate the uncertainty on the number of clusters in a posterior on N, which is the orange plot. And so we have an hypothetical estimate of N, in this case, around 2,100. And you can also observe the false negative rate and the false discovery rates, which are quite small. So this is just to show also the record linkage performance in this situation. In the paper, you can find also a very substantial sensitivity analysis where that confirms what we said before. That is that increasing the prior mean and the variance of the distortion probabilities, we have a strong reduction of the posterior mean of the number of different entities and a consequence increment of the cluster size. In particular, the posterior mean of K's, which from the corrected value of 450 microcluster to also inconsistent values. Anyway, the positive aspect of the sensitivity analysis was that the effect of G is negligible with very small, with a very small impact, and especially is negligible if we consider the impact of n in a fixed analysis where, in analysis where this quantity is fixed and let to vary. The impact of n is substantial in this case. We also just practically, well, better to see better the strength of our possibilities, we also apply the model basically with all the prior settings that we have seen before, also to the RL10,000 dataset, which is a larger dataset, where we implement a block analysis. In particular, we divided the dataset in 10 blocks of sites 1000, where each block had approximately 800 single clusters. And here you can see the posterior for K. Say that the true number of K is around 100, are the red points in the first plot on the left. And you can see that the posterior of K are driven by the true number of clusters. And anyway, there is always some bias in these estimates. In particular, it seems that the true number of K is underestimated by our posterior distribution. And in particular, when we observe a larger bias, we also observe higher false negative and false discovery rates, as Jared has noted in the discussion. And this, anyway, can be, an element for thinking about some corrections driven by the false negative rate and false discovery rate, in particular for the estimates of n, which in our framework can be the interesting parameter. Okay, now let's go to the last example, which is the Syrian dataset, and we concentrate on the victims in a single province, that of Raqqa. And we notice that there are some difference in the list. For example, the VDC list provides directly the English equivalents for the Arabic names, while the other list provides the Arabic directly the Arabic names. So we need to obtain the corresponding English name by software transliteration, and this created an additional noise in a single list that we didn't consider. Anyway, after a preliminary data cleaning, we end up with a list with more than 1,500 records, and the other list with at the end approximately 1,000 records. And we use first and family names transformed again by the Soundex algorithm. And at the end, we had 11 key variables because we didn't divide the year in four subfields, basically. Okay, for this data set, as an exemplification, we provide 3 different analyses. In the first analysis, we considered the 2 lists as separated lists, and so we fit our model to the single list one by one, basically. So in this case, we can say that only within list duplications were allowed. In the joined list analysis, this is the framework that we propose in the paper. So we fit the model jointly to both the lists. And also we did a sort of record linkage where only between lists duplication were allowed. But basically, this record linkage analysis was done by during the updating of the conditional distribution of lambda, just permitting duplications across the list and not duplication inside the list. Anyway, here we report the distribution of the cluster size average across the MCMC simulations. So, for example, in the separated list, you can see that we are just around 50 clusters of size 2 inside the first list, around 40 clusters of size 2 in the other list. Okay, I will go back on these numbers in a while. Here you can see the posterior, here you can see the posterior on N that we obtained with our model, and the flat posteriors are those obtained with the with the separated list analysis. The black line is that one obtained with our proposed model, and the red dashed line is the one proposed by our version of the record linkage. Some comments on this analysis. In the separate analysis, the two lists alone provide slight evidence for very large value of N due to the small within list duplication rates. You can see here that we are just 50 and 40 clusters of size 2. And so this is in line with a large population, with a population with a large number of entities. When we introduce the joined list analysis, the duplication rates increase a lot. So we see a lot of duplications, and this is in line with a reduced population size, which is the black line that you see here. Note also that in the proposed record linkage analysis, we are eliminating the evidence of within list duplication. So we are saying basically that in each list, only all the records are due to different population entities. So with respect to the joined list analysis, it is correct that we increase the estimate of N. And it is not reported in the paper, but it's possible to see that a proper record linkage analysis where the model does not account for within list duplication rates would decrease the N estimate, basically. Okay, there are some questions because we are just 2 slides for the discussion, and let me know if I can go on for other 2 minutes.
Please go ahead. So the discussion is, I mean, there are no questions.
No, this is the discussion of the paper, not, well, it's just 2 slides to conclude the presentation of the paper, okay?
Perfect. Yes.
Okay. Okay, just to recall some theoretical properties that are in the model that we have proposed. In particular, we want to stress this fact that in our model we are able to find the prior expectation given N of the number of clusters. Given N, and you can see the formula that are here in the slides. We notice that when N is fixed and when the capital N is fixed and the small n is going to infinity, At the end, we are seeing in the prior that we observe all the population entities, okay, because the sample size will increase and will go in the list all the n population entities. And so effectively, the expected value of k given n will convert to n, and the variance will go of k given n will go to 0. Similarly, in an opposite way, when the small n is fixed and the capital N is going to infinity, we are in a opposite situation where at the end we observe, of course, all different entities because we have an infinite populations, and with a with a fixed sample size, we observe all, a priori, all different entities. These quantities can be compared with similar expectations that can be found, for example, in the Maurizio paper, where a prior, a uniform prior on the partition space is used. Similarly, I go very fast, it's possible also to change completely the prior modeling, for example, by using something more related to the classical Bayesian non-parametric literature, in particular via a Pitman Yor prior, because also in this case we have, for example, a prior unexpected value, a prior expectation on k, and we can select the parameters of the Pitman Yor prior in order to control a priori the number of clusters. And we did this in another paper where we investigate the impact of the duplication process into the regression framework. And of course, it's completely different, but I can skip these slides. So I just conclude with 3 points, and one point that we want to highlight is that in our opinion, something is working in this model because the HitMIS model provides a computational tractable marginal distribution for the cluster observations. Of course, it's important, it's necessary to investigate the impact of other prior on the partition structure. And this was our, first, was just a tentative to start with a proper analysis of this kind. And of course, as was noted by all the discussants, it's evident, it would be important to extend our approach, introducing both heterogeneity and dependence in the sampling probability of the population units, as in the usual capture-recapture, and also to introduce measurement error that could be covariate or least depending, as in the Syrian data application, where one list had for sure a greater measurement error. Okay, thanks a lot to all of you. And
okay, perfect. Go ahead.
Okay, do we have my slides here?
Yes.
Great. Okay, so I just want to take a second here and thank Michele for the invitation and for the opportunity to discuss this wonderful paper. Like Maurizio, Brunner and Andrea's original paper, or one of the original papers in AOAS, was sort of the one that got me started down this path of working on record linkage and deduplication and related problems. So it's great to see that work continuing, and it's great to see that work continuing with an increasing population size. It's also really nice to be on here with Becca and Maurizio, sort of products of that CMU record linkage pipeline headed by the late, great Steve Feinberg. So kind of nice to have us all more or less in the same place. So I'm going to talk about sort of two main themes that I was thinking about as I was reading this paper. The first one is just related to this idea of joint modeling of record linkage and deduplication, plus the downstream task, sort of whatever we want to do when we put the files together. And the second theme is about how we measure and improve performance in our methods. So, these are in a lot of ways, obviously sort of direct responses to the paper here, but these are two sort of great big threads in the literature here, stuff that I struggle with in my own work and things that I hope that we can all be thinking about together as a sort of a broader community here. So I'll start off by talking about kind of theme one, the promise in the peril of joint modeling. So the paper that we just saw presented proposes a joint model for de-duplication, which I'll sort of restrict to thinking about removing duplicates within a file. For record linkage, which I think about as identifying different records across files that actually match to the same person. And population size estimation in this case. We call that sort of a downstream task, the things that we want to do with that file that was properly linked and deduplicated. So there's obviously a lot to recommend tackling all these problems together. The biggest one is just that we get coherent Bayesian inference for all those quantities, right? So if I'm interested in population size estimation, I can look at the marginal distribution, the marginal posterior distribution for the population size n, and I get inference that makes sense in a particular way. If I'm interested in other stuff, maybe I'm actually interested in sort of the overlap between files or other kind of functionals of that record linkage structure, I also get coherent inference for that too. So that's the good. The bad is that it's really difficult to specify big models and their prior distributions, okay? So we saw some discussion of that when the paper was presented, these issues of choosing these measurement parameters, really having to kind of nail those down with informative priors, just because this problem is so big and high dimensional. And obviously, the more stuff that we sort of bolt onto our models, the more difficult it gets to be to think about specifying those models and writing down prior distributions for them. So in particular, there's this tension between how expressive our joint model can be, how flexible it can be, sort of the fewer assumptions that a model can make, the better in general, I think. So there's this tension between having a model that is flexible and expressive versus a model that we can actually interpret. So in the paper, the authors derive all these nice properties about prior expectations on the population size, prior variances on the population size, things like that. Those sorts of things are really only tenable if the model is kind of simple enough to do some math, right? And then, of course, we actually have to fit this model, right? So at the end of the day, once we write it down, we're going to need to be able to do MCMC or some other posterior approximation technique to actually do inference, right? So there's this sort of inherent tension there. And, I'm thinking about here, not just necessarily record linkage models in specific, but, I've got a background in missing data and multiple imputation, where we're sort of thinking about specifying big joint models for missing values in general, not just the special case here of the missing values being the linkage structure, the de-duplication structure. And we run into this all the time. Another sort of subtle issue that arises when we're fitting joint models like this is the potential issue of kind of feedback between submodels. And I'm not going to be real precise about kind of what this means, but I'll just point out one specific instance of feedback between what I would call submodels here. And that is that the kinds of sampling assumptions that are essential to be able to do population size modeling actually imply very specific prior distributions on the record linkage model, okay? So just kind of thinking simply about this, if we're going to fit a population size model that assumes that the files are simple random samples from some population, well, that actually implies a very, very particular prior on how much the files in the question are going to overlap, the probability distribution of the number of entities that they're going to share in common, right? That's sort of intuitive. But if we think about contrasting that with models just for the record linkage task or the record linkage plus de-duplication task, that's a case where actually those assumptions about sampling from a population are almost irrelevant, except to the degree that they inform the prior distribution kind of on the amount of overlap there. Okay, so that's a case where sort of expanding this model, we actually have to layer on some assumptions that maybe we didn't need to do to solve one of these subtasks. That feedback can be a little bit pernicious. So a little bit of a specification in that population size model might not be important when we actually know the record linkage structure, when there's no issues about duplicates or looking across files. But once we don't know that, and we're kind of bouncing back and forth between inference on the population size and the record linkage and the de-duplication, you can get these sort of feedback loops that can degrade model performance. And this is an issue generally in the context of fitting big joint models. So that's kind of the perils that I'm thinking about when I'm writing down big joint models. By the way, I shouldn't say that I'm advocating against fitting joint models. It's something that I've done in my own work, and it can be a really effective strategy. But I think we have to be sort of clear-eyed about what we're doing and the potential drawbacks. So what could we do instead? So I think most of the alternatives to joint modeling take this sort of form of two-stage modeling or inference. Okay, so in this particular context, what would that look like? So we can imagine treating that map that would give us perfectly deduplicated and linked files, which is a parameter called lambda in the paper. We can think about just treating that as missing data and trying to do this sort of two-stage inference. Okay, so in stage one, we could obtain a posterior distribution or sample from a posterior distribution over lambda to get draws of completed, deduplicated, and linked data sets. And then in stage two, we could fit whatever population model that we cared to. We could compute a posterior distribution for that for each draw of that lambda of those completed data sets, and then actually combine those posteriors by averaging them. Okay. So this is a case where it would have been nice if Mauricio's microphone had been working, because this is actually related to some work that he's done. So when those two models are consistent in a sense that I'm not going to try to make precise, or compatible in a way that I'm not going to try to make super precise, all we're doing is we're representing that joint posterior over the population size and the sort of that map giving us the deduplicated and linked data files. We're taking that joint posterior and we're sampling from it by composition. So in that first stage, we're getting a marginal posterior distribution over the links between data files. And in the second stage, we're getting samples or computing the posterior distribution for the population size, given deduplicated files and of course the data, right? So that procedure I outlined before is really just computing the marginal distribution for n under a model like this, integrating out that parameter lambda. Okay, so this is actually kind of a nice way to think about the problem. In particular, a marginal distribution for the linkage structure lambda could be compatible with multiple different models for the population size, given a completed data set, what I'm calling P2 here. And so if we have a recipe for doing this, we can actually get inference for multiple different population size models under one set of posterior samples or one posterior approximation for lambda. So Mauricio's actually thought about this very carefully. He's outlined how to do this in his 2018 AOAS paper here that, in my opinion, doesn't get the attention it deserves. So trying to highlight it here, and I hope that he'll talk about it too in a second. Excuse me. So there are obviously some conditions that need to be satisfied here. There are some conditions under the separability of the parameter space in the models that I haven't put here. But a little bit more intuitively, we need the assumptions in those two models to kind of agree. So if P2 is going to assume that the files under consideration are simple random samples from some population, then P1 better have a prior distribution on lambda that reflects that, right? Otherwise, it's not entirely clear what we're going to get. But I think that's actually a really interesting case to think about. So what kind of inference can we expect to get when the two models are sort of incompatible in that way? You know, I'm sort of glossing over a lot in the notation here, but I think you could just observe that we could always take that marginal posterior distribution for lambda and kind of bolt on a new posterior distribution for the population size given lambda in the data. I call that here P2 star, the star just to sort of denote that we're not actually getting that from this joint distribution on the left. Okay. And then I think there are a lot of interesting questions here about what we actually get when we do this sort of two-stage modeling. So we have this P2 that's not necessarily compatible with the joint distribution that we would have written down if we had all the data at once. But I think this is a really relevant case for practice because this is what's going on in a lot of record linkage contexts. In particular, if you think about contexts where the person doing the linkage is not the same as the person that's doing analysis, or the person who's doing linkage is actually trying to serve multiple different data analysts at once. It might be the case that Becca has one model for population size and Mauricio has one model for population size and I have another model for population size. And those three models are maybe not actually compatible with each other. But we might want to generate one set of links that can support analysis of those three models, at least in some reasonable way. Again, this is related to a lot of issues that come up when we fit joint models. This is something that people have thought about a lot. This Jacob et al. Paper sort of casts this in the framework of modular statistical modeling, and come to the conclusion that these sort of modular approaches can actually improve on joint modeling when the joint model is specified. In my opinion, that's almost always going to be the case. There are lots of ways that we can specify a big joint model, and of course, the bigger the model gets, the more likely we're going to get part of it wrong. And of course, the drawback here is that that sort of modular approach can be inefficient when the joint model is actually correct. We sort of don't get that feedback from the population size model actually informing what's going on in the record linkage model in the deduplication model here, this P1 of lambda. Okay. I just want to point out that there's some sort of interesting connections here to the literature on uncongeniality and multiple imputation. That's a connection that doesn't seem to get made very often, but if you're familiar with the missing data literature, you have sort of the same problem here, where the imputer and the analyst are not the same person. And how do we actually combine these two posterior distributions to get reasonable inference? And there are some answers there in the uncongeniality literature, some conditions under which we can at least get conservative inference in that second stage model based on some conditions on the first stage model. So I think that's sort of a fruitful area for future research. Okay, kind of the second theme here was thinking about how we measure and improve performance. And there are kind of four main bullet points here that I'm going to run through really quick, just in the interest of time. Okay, so the first thing that I want to point out is that when we're thinking about measuring and improving performance, if we're going to do that by fitting our models on benchmark data sets, they should be representative of the applications that we care about. I'm going to actually make the argument that the RL data sets, despite being easy to access and easy to work with and easy to use, are really not representative of the kinds of data sets that we see in practice. So I'm showing you here 5 sets of duplicate records in the RL data, in this case 10,000 data set, but the 500 data has the same sort of structure. And if we look at the duplicates and the errors that are introduced, we can see that they're very, very mild. Okay. So for each pair of duplicated records, you're going to have one error introduced somewhere in the fields, exactly one error. It could be substitutions of characters here, it could be insertions of characters like down here in the Ursula. It could be flipping one of the numbers in the birthdays or the birth month, day, year, things like that. The point here is that if you actually were to look at some of the duplicates here and some of the duplicates that have been identified in the Syria data set, I think that you would come to the conclusion very quickly that the Syria data are much noisier than the RL data. And that's been true for all the real data that I've looked at in practice. Okay? So we want to be a little bit careful when we're using these benchmark data sets. I've used these data sets myself. They're sort of useful as giving us kind of a baseline that everybody in this literature is familiar with, but we shouldn't be confused about performance on RL data generalizing to performance in applications, of course. When we're presenting new methods, we always want to compare them to baseline methods, even if we're just running a horse race against a dead horse. And that's kind of what I went ahead and did here for the authors. So I'm showing on the left-hand side, I'm showing that plot that we saw in the talk of results on the RL data 10,000 example across 10 different blocks.
Hello?
Sorry?
No, okay, sorry, Jared. It's Mauricio and I, we are trying to see how things work with the, okay. I think we are fine. I got what happened. Sorry about that.
Okay. Oh, no problem. No problem. So I'm showing here the results that the authors presented on RL data 10,000. And just to compare, I fit this little model that I introduced in a paper a couple of years ago. This is not a particularly good model. In fact, I would say that it's actually a pretty bad model. The point of working with it in that paper was because I could do some math basically and kind of illustrate what happens when we fail to take into account pre-processing in record linkage problems. That's sort of neither here nor there. The point just being that it's a model that's really easy to write down, a model that's really easy to fit, and of course a model that doesn't give the same kind of rich inferences that the model in the current paper does. So I don't want to put this as some kind of competition. But I think it's useful to understand sort of the baseline level of performance that we could expect from a record linkage model when we're developing and presenting a new model. Okay. And in this particular case, because that RL data is so clean, we can actually do really well with baseline methods. Okay. So on the right-hand side, I'm just reporting a plot of the performance of my sort of tweaked Pileggi-Center model as we vary the Pileggi-Center cutoff. If you're familiar with that, that'll probably make sense. If you're not, I don't really have time to explain it. But just recognize that each data point here represents performance on this data set for a different decision rule based on my model output. And what we see is that actually using that model, we can get down to a 4% false discovery rate or a false match rate and a 1.6% false negative rate or a false non-match rate. If you sort of compare and contrast that with what we're seeing across those blocks, and these numbers here are averaged across those 10 blocks. If we compare between the two, then we can see that actually this simple baseline model does quite a bit better on the record linkage task, or sorry, the record linkage and deduplication task alone. That's not to say that this is a better model, because it doesn't do all of the great things that the model in the current paper does. But I think we should be a little bit cautious about presenting a new method when it doesn't, or presenting a model that proposes to do joint inference for population size, record linkage, and deduplication, if we don't get at least sort of reasonable performance on relative to existing methods from one or more of those subtasks. Okay. The other point I want to make is kind of obvious, but I think it gets ignored a lot in the literature, that there's just no substitute for measuring error rates on the data set that you care about. Okay. So I won't go through all these bullet points in detail. I'll just point out that it's difficult to estimate false non-match rates. So, you know, in general, most of the decisions that we make about record pairs in a particular data set is going to be that they don't match. But it's actually relatively easy to get pretty robust estimates of false match or false discovery rates by labeling randomly selected matches. And I sort of make an argument in the paper for some ways that we should design those experiments. I don't think it's worth going super in depth on those right here, but just to point out that, that we can do this. Most of the papers in Bayesian record linkage that I see actually don't do this. We have some evaluation on a benchmark data set where we know some ground truth, some synthetic data, but we don't actually go on and in our application, the one that, you know, the data analysis that we nominally care the most about, we don't actually go on and go through this labeling exercise to try to estimate false match rates. And of course, in the context of the current paper, there are actually several different versions of false match rates, right? There's falsely identifying a duplicate within a file, falsely identifying a link across files, et cetera. Those have different implications for the downstream task, and we should think about trying to estimate and understand those. You know, I think this is particularly relevant when we think about the model performance. So again, looking at the performance across those blocks in the RL data 10,000 example, what do we see? Well, if we focus on the top left panel here, where we're looking at K, the number of unique entities contained within the file, we see that actually in several of these cases, the model is very confident and pretty wrong, right? So we see true values that are kind of way out here in the upper tail of the posterior distribution, and the posterior is concentrated at a value that's below that. You know, you could sort of quibble about whether the difference between 10, 20 records, whatever, is meaningful. But I think that propagates over here into estimates of the population size in sort of an obvious way. Okay. And if you want to think about why that's happening, it's pretty clear once you look at the error rates and think about what this quantity is. These are contexts where we're actually identifying in those blocks, we're identifying a high proportion of false matches. So something like 15% of the matches that we're making on average within those two blocks are incorrect, which is biasing down the estimates of the number of unique entities within the file. So that bias is coming from sort of an obvious source of having high error rates. You would never know this was going on if you didn't go to the trouble to estimate error rates in your particular application. Okay. So I think that's really important to do. It raises the next question of if we actually fit our model, we do our best and we have error rates that are high or relatively high or higher than we would like, can we adjust our inferences for those error rates? And I think the answer is sometimes. So there are estimates for population size that account for linkage error rates. The best ones that I've seen are relatively simple in that they only sort of look at two files and they don't necessarily think about duplicates within the files. But based on the results here, it seems important. And I'll just share an example where we were able to actually make an adjustment. In our paper, McVeigh, Spahn, and Murray, we were looking at estimating party switching rates. So we link two voter registration files and then we compare and we just try to compute the proportion of people that switch their party affiliation from Republican to Democrat or from Democrat to Republican. And this is kind of a nice case where we're able to do some sort of quick back of the envelope calculations and understand the effects that given levels of a false match rate would have on biasing our estimates and try to correct for that based on estimated false match rates. So I'm not going to talk in detail about what this picture is, obviously, but we have three different estimates. We have an unadjusted estimate on the left, we have an adjusted estimate in the middle, and then a different adjusted estimate that assumes a higher false match rates sort of on the right. Ignore the squares, those are for a different method, and focus on the violin plots. What I want to point out here is that uncertainty due to the effect of linkage error, in this case, was actually greater than uncertainty due to unknown links across the two files. Okay, so I think that the effect of linkage error, the effect of models that are not doing the record linkage job perfectly on our ultimate inferences should be more a topic of study than it often is. And I would say that, you know, this is sort of an opening salvo in that war. I think that thinking about that in the context of population size estimation with linked files, for regression with linked files, I think there's a lot of work to do here and I would sort of encourage everybody to train their sites on that. Okay, so with that, I'll stop there. Thank you again for inviting me to discuss this wonderful paper. That's my email, my website, if you have any questions for me after the session.
Thank you, Jared. I think it is also a good time to tell people that you're going to be here again in September, right? For the discussion paper of the September 2020 issue of the journal, which will be about one of your manuscripts that have been published in Bayesian analysis with Richard Hahn and Carlos Carvalho, Bayesian regression tree models for causal inference, regularization, confounding, heterogeneous effects. We are now accepting contributed discussions that should be submitted to the journal using the electronic journal management system before July 31st, 2020. We have also been able to fix the issues, hopefully with the voice with Mauricio. So I will leave the word again to Mauricio Saville for his discussion. Okay, let's see. I'm gonna unmute you. Let's see. Mauricio, you are now muted. So I don't know. I try to unmute you from my side. Okay, now you should be going. Okay, so Mauricio, go ahead with discussion paper by Andrea, Rebecca, and Brunero. Still muted. Let's try again. We cannot hear you. Try to mute yourself.
Hello.
Perfect. Now it works. Fantastic. Thank you. Mauricio?
Can you hear me now?
Yes, we can.
Okay, let's try. Okay, sorry about that.
No problem.
Technology is, it's too much for me, apparently. Okay. Yeah. No, I need to upgrade my internet service, apparently. Well, okay, so, let's get back to this discussion. So I was going to give you a big picture, or I guess the way in which I see the big picture where this paper lands. And so let's imagine that we have an analyst that wants to estimate the population size. They determine that the way to go is use capture-recapture multiple systems estimation, because they have multiple samples that are available on multiple data sources, collecting information on potentially a subset of that population that they are interested in. Now, they might have information about how those data sources are collected and how they might relate to each other. For example, in the case of the human rights data analysis group, they know or they have information about how these organizations in Syria cooperate with each other, how they, maybe their ideologies or what their objectives are. And so they might be able to think hard about about what a reasonable capture-recapture model or what some reasonable assumptions might be in that context. Now, the problem is that they don't know who is who across these samples, right? Or across these different data sources, or even within the same data sources. That's the case of duplicates. Ideally, they would like to have just a unique ID, a perfect unique ID, and so they will just simply use that to deduplicate and to link the different samples, and they would just focus on the capture-recapture model. So that's let's say kind of the big picture where I think this paper lands. Now there are multiple approaches to capture-recapture, right? Like, so there are like lots of different methodologies for doing population size estimation. Here, just some common references to the literature. But the point that I want to emphasize here is that if the analyst didn't have to deal with the record linkage problem. What they would really be interested in would be, let's say, using one of these methodologies for estimating the population size. So how do analysts, let's say a relatively sophisticated analyst, tackle the problem? Well, so, if they don't have this unique ID, I think what most people would do is they simply use some ad hoc, or let's say some practical way of linking and deduplicating these data sources. And they would just simply ignore the fact that there might be any errors, or ignore the fact that there is some uncertainty in the linkage process, and they would simply proceed with the capture-recapture model, right? Because what they really want to do at the end of the day is to estimate this population size, and so they might put more emphasis on the part of the capture-recapture model. In some sense, the linkage and the duplication part is some nuisance that they just have to deal with somehow. That's, let's say, an analyst for whom really the final goal is to estimate this population size. So how could, let's say, where does the contribution of Tancredi, Steorts, and Liceo fall, in this kind of in this framework, or in this context? Well, so the approach proposed by Tancredi, Steorts, and Liceo, well, it builds on a framework for record linkage and duplicate detection that was started by Rob Hall, who was a student of Feinberg. So this paper, Hall et al., that's Hall, Steorts, and Feinberg. Then Rob Hall left academia, so they took the endeavor of pushing this framework forward. And so there are also some connections with the work of Tancredi and Liceo that they did in the early 2010s. But so they, as Brunero mentioned earlier in the presentation, the contribution that this paper makes from the model point of view can be seen as putting a prior on a hyperparameter in the model of Steorts, Hall, and Feinberg just in 2016. In that paper, that hyperparameter represented the number of labels that you use that are available for labeling partitions, where the partitions represent groupings of the records according to the different entities that they refer to. But in this new contribution, they provide a justification for why that parameter now can be seen as a population size, and so putting a prior on that population size, well, it's a reasonable step. Now, so that leads to a joint model for, or you can see this as a joint model, of course, for a record linkage and population size estimation, including, of course, deduplication. And so there are two ways in which this model is justified, or let's say two characteristics that this model has. One is that if the partition of the data files is known, that is, if you know who is who across and within data files, then this approach corresponds to a capture-recapture model where there is one capture occasion for each record in the data sets. So typically in capture-recapture, you have, let's say, K multiple capture occasions represented by the list or by the samples that you have. Here, the interpretation would be, or one possible interpretation is that you have a capture-recapture model where each record kind of corresponds to its own sample in some sense, or its own capture occasion. The other justification was given by Brunero earlier today, where we have a data generating process where each individual in a finite population is subject to a Poisson distributed random number of capture attempts. So now here's the way well, some criticism that I have for the approach, and is that the capture-recapture component of the proposed approach really does not correspond to any commonly used model for population size estimation. So the assumptions of the, let's say, the capture-recapture component of the model are too stringent. So from my point of view, I think that developments in this area should accommodate commonly used capture-recapture models, because otherwise analysts won't use them. I mean, let's keep in mind that the target audience, let's say, of these type of methodologies are people who will want to estimate a population size, and they just somehow have to handle the record linkage part, but that's not really their main goal, right? Their main goal is to estimate a population size. If they have a unique ID to link and deduplicate, they wouldn't, I mean, they would be super happy, and they would focus their effort on the modeling, on the capture-recapture model. So now we could see this as a sort of first step for more, let's say, complex contributions to this area, where you create joint modeling approaches that combine different record linkage approaches with different population size estimation models. But as I mentioned in my discussion, the thing is that I think each single combination that you might think of a record linkage model with a population size estimation model, that will have complications that you need to figure out on a case-by-case basis. So it's not really, I mean, it's not, I think you still have to figure out how to do that for every case that you want to, for every sort of pair of models that you want to put together. And I think there might be some overlap in this part, what I'm going to say now, with the discussion of Jared. Because you can imagine that, you know, a natural future endeavor, given what was presented here, and maybe given the paper of Tancredi and Liceo back then in 2011, you could imagine that, you know, you could pursue publishing a paper for every single, you know, that combines every single model for record linkage with every single capture-recapture model, right? So you have a giant number of articles out there where you, for each article, you put two models together. But the thing with that is that for each pair of models that you put together, you still have to figure out how to, for example, do approximation of posterior distributions, right? So you have to tailor MCMC schemes for each of that combination. You know, so but you can imagine that this could lead to a plethora of articles, and not only capture-recapture models, right? Like you imagine every single record linkage model being combined with every single model that is used for statistical analysis. And each of these combinations could be a separate paper. That could be, you know, like something that will inundate the literature with different, you know, approaches and different combinations and how to do each combination. I think that we don't necessarily want to see that, right? Like we want to see more meaningful contributions that develop general approaches that allow users to combine pieces, you know, like modeling approaches for record linkage and modeling approaches for capture-recapture, kind of in a way so that they can accommodate, you know, different pieces, kind of in a very easy way. How to do that? Well, there might be classes of capture-recapture models that allow you to do that. You know, you might have a template where you obtain different capture-recapture models as particular cases. Of course, that will require developing software that makes all of that readily available for users. Now, an alternative endeavor would be to develop approaches that allow users to reuse record linkage results for different capture-recapture models. So one example of this is an approach that I proposed in this paper in 2018 in the Annals of Applied Statistics. This is an approach that has a feeling similar to a multiple imputation. There are some technical differences between what is being done here and what is done in the missing data literature, but the idea is as follows. You need a record linkage model, a Bayesian record linkage model that gives you a posterior distribution on partitions of the data files, where these partitions represent groups of records that refer to the same underlying individuals. But this approach could be one of the approaches that I have proposed, or maybe one of the approaches that Steyers, Hall, and Feinberg have proposed throughout the years, or it could be anything else that someone might come up with later on. You need, on the other hand, a capture-recapture model that has sufficient statistics that depend only on the overlap of the data files in terms of their individuals. That is, the capture histories in this literature of capture-recapture. And there are multiple models that satisfy that condition, right? So throughout the years, there are many models that have that condition. And it could be any other model that someone might come up with later on. But the point is that these are the models that the analysts will want to use anyway if they didn't have the problem of the record linkage and the duplicate detection. Now, the procedure is very simple. You obtain a posterior sample of the coreference partitions, that is the partitions that give you the links and between records from your Bayesian record linkage model. Then for each of those posterior partitions, for each of those, you could think of that as if it was your unique ID. So based on that, you should be able to run your capture-recapture model. So for each of those, you estimate the population size given your favorite capture-recapture model, and then you average the posteriors for the population size that you obtain. Under some conditions, it turns out that this, even though this is a multi-step procedure, it actually corresponds to a joint Bayesian model. So that's a nice advantage because it gives you the flexibility of doing things in a multi-step way, but you still have the justification from the point of view of an underlying joint Bayesian model. Now, another advantage is that the results from the linkage can be reused for different capture-recapture models, right? Because essentially, you do the linkage in the first step, and then you feed them into the population size estimation step. But then that second population size estimation step could use different capture-recapture models. And of course, it allows model exploration because you don't have to kind of derive a specific MCMC scheme for each combination of record linkage and capture-recapture models. Now, the disadvantage is, of course, that you're combining two modeling pieces. So really, the quality of the overall procedure will rely on the quality of each of the individual pieces. So if your linkage model is not good, so your final result is not going to be good. The same thing for the capture-recapture model. Another characteristic is that it doesn't really allow capture-recapture models with covariance. But I think developments along these lines are worth pursuing, and I will welcome having more brains thinking about how to do things in a multi-step way so that it can be more practical, and so hopefully we can make progress along those lines. Some final thoughts. Regardless of whether new developments come in the form of joint models or two-stage approaches, and each of those things have, let's say, pros and cons that we can discuss. I believe that that these approaches should be applicable in the sense that they incorporate commonly used capture-recapture models, because then otherwise analysts who really want to estimate population sizes, they might not potentially use whatever we propose. And so that's the end of my discussion. Again, I want to thank you for the opportunity, to be a discussant of this work. I look forward to future contributions to this area from the authors, Tancredi, Liceo, and Steo.
Thank you, Mauricio. We have had two very nicely put discussions. I'll leave the word to Brunero, Andrea, and Rebecca for the last word with some rejoinder, and then we will have a quick discussion, or maybe open discussion to have it, including the attendees. Please, if you have questions, use the Q&A section.
Michele, could you give me the screen share as I'm going to do the rejoiner?
Okay, perfect. Sure.
Thanks so much. I'd just like to thank Michele for organizing this discussion, and also thank Mauricio and Jared very much for the nice discussions, as well as Christian and the contributions of Ju, Biswas, Jacob, Mina, O'Leary, and Palm.
Perfect. Are you able to share the screen?
Just a moment. I think so.
Perfect.
Can you see?
Yes.
Okay. So I won't have time to get through all the points. But hopefully I will get to most of the ones that were covered. And hopefully then we can cover some of the other ones in the final discussion. So the organization of the rejoiner, we have grouped into prior modeling, joint modeling and inference with linked data, computational issues, and then model and performance evaluation. Just as a quick recap, I'm going to do a review of the model and some simplifying assumptions. So for the rejoiner, we're going to assume just one single list and database just to make things simple. We're going to assume that the error probabilities depend on just the key variables and not the population entities. We're going to assume the probabilities theta L are going to be known. And then conditional on the true values, V tilde J prime.
I noticed that as well. So Rebecca, for some reason we lost the screen share.
Okay. Just a minute.
Maybe the best is
for some reason my browser's not letting me screen share.
Oh, maybe you want to share the desktop?
No, I'm getting a weird message from Zoom that says your browser's preventing access to my screen share.
Oh, interesting. The first. Okay, let me
try a different web browser.
Okay. I can try to do. Okay. I think we've had all the possible issues with Zoom during this webinar. It's the first time actually that this has happened to this scale. But it's what happens when you do things live. So
I'm Brunero from Rome. If it's okay, I can show the slides and Rebecca can comment on them.
that is perfect. Okay.
Yeah. Okay. So I'm going to share my screen now.
Okay, perfect. Let's see. I have oh, Rebecca has joined. Let's see. Oh. Let's see. Rebecca, is that okay if we do that? I saw a message from you, but I do not. Oh, okay. I see now what you mean. Okay, maybe we enter within a different account, I think. Okay, we can try to do this. You should be able to share now, Rebecca. Is it working?
Yeah.
Perfect.
Can you see?
Yes, we can. Okay.
Okay, perfect.
To cycle back a second to reorganize
Can
things.
everyone hear me and see me?
Yes.
Okay, great.
Go ahead.
So I was just reviewing the model and the simplifying assumptions. So just quickly, we're assuming one single list. We're assuming that the error probabilities are just depending on the key variables. We're assuming the probabilities theta L are known. And then conditional on the true values. So this is V tilde J prime. The statistical model will reduce to what we have here in equation 1. And then this function K of the observed variables and the true variables can be written as this hit and miss model from Kopis and Hilton. And so this is just stressing the analogies with the mixture model that was noted by many of the discussants. So it's nice that Jared mentioned the perils of the prior on the linkage structure, and the choice was consequential. And this is one point that we wanted to discuss. So this will tie in nicely with the discussion that he already made. So just a couple of things that we wanted to emphasize is that in a previous paper that I worked on with Rob Hall and Steve Feinberg, we treated n here as a fixed parameter. Then in the paper with Brunero and Andrea, we propose a prior on n here, where the model is more flexible and the uncertainty of this particular quantity is going to propagate into the record linkage task. So under our proposed model here, there's a partition Z, and this is induced by the mixture model that I just showed in equation 1 on the previous slide with an unknown n. And we'd like to stress that we have not stated that the distribution of the partition Z nor the expression after eliminating n represents the correct model in a real de-duplication application. So we didn't stress this in our original article, and we're stressing this also in our rejoiner. So the perils that Murray, that Jared have kind of stated are actually shared by other proposed record linkage models also in the literature, which I'll go into next. So Sedinle in 2014 has proposed a uniform prior on the co-reference matrix. It's a different type of uniform prior, and we go into more details of what this is specifically in the rejoiner. And in the 2016 paper with Hall and Feinberg, we illustrated that both of these priors are highly influential. And much of the Bayesian record literature actually assumes a uniform prior on the linkage structure or a co-reference matrix if they're taking these types of approaches. And so we're just kind of summarizing that these are quite heavily used in the literature, and they're quite standard, even though they're influential. So our kind of question back to Jared is why should these particular models be considered, I guess, to be less dangerous than the ones that we're assuming? Kind of going into joint versus two-stage models. So Mauricio brought up a great question of how should one handle these in practice. I think this really depends on the application, as Mauricio mentioned. And I'm just going to briefly touch on this because one could have probably an entire day's discussion regarding on what approach you could take. So for scaling the joint model, I think there's some really nice approaches, such as the ones by Zhu et al. In their discussion that could be potentially useful for scaling these joint models, or some recent ones by Marchand et al. Using a partially collapsed Gibbs sampler. Of course, one could take these two-stage approaches, and you could use the one on the linkage averaging, which is very nice, by Sedinle in 2018, or even a paper by McVeigh, Spain, and Murray from 2020, and there's other approaches. As Mauricio mentioned, oftentimes you're actually wanting to assign a unique identifier, and you might want to do this using an approach by Kaplan et al. 2020, or extensions in a completely fully unsupervised way. So I think there's many different ways you could approach this type of problem, and neither one is more correct than the other. Now kind of going into the joint modeling and inference with the linked data. So Sedinle noted, unfortunately, the capture-recapture component of the approach proposed by the authors does not correspond to any commonly used model in this area, and its assumptions are too stringent to be practically useful, as acknowledged by the authors. So Mauricio went into a lot of details in this in his discussion, and so we just wanted to come back to this, as we thought this is an important point. So one thing you can do is, if you're conditioning on the list sizes, we're actually able to obtain a conditional likelihood similar to that of a paper by Dirac from 1958. So if you fix the sample sizes, this eliminates the capture probabilities. So this then leaves the unique parameter, the population size n. Then if you condition on the absence of within list duplications, the lists become independent, simple random sample without replacement. So hopefully this will satisfy Mauricio. Then the number of matches between two lists will actually follow a hypergeometric distribution, as in the original paper by Tancredi and Liceo from 2011. I thought Jared posed some very important and interesting questions that I'm just going to quickly summarize below. Is it time to leave RL data alone? So that's how I thought that's how we thought he had posed it in his discussion paper. Should researchers do extensive labeling of data sets? And should we have done evaluations to methods such as Filigi and Center, Sedinle 2014, and Stortz 2015? And so I'm going to just quickly go through these 3 points. So RL data, I think this is an interesting question. I would lean towards not leaving it behind, because it actually illustrates a very good point that was picked up by Zhu and colleagues, that it illustrates when samplers are slow to mix and when you have convergence issues. And I think this is a very important point. I think Jared picked up on another important point regarding RL data is very clean. So it's very important, to be cautious regarding these benchmark data sets, and perhaps to utilize more of them in your papers moving forward. But I don't think we should leave it alone, because it's very slow to mix regarding the fact that it has very few duplicates in it. It might be better to have another constructed data set that's slow to mix and also has a large amount of noise, and these can be constructed. The labeling issue is a very important question. For this particular data set, we didn't do labels because we felt that it would muddy the waters. So experts from the human rights data analysis group have already labeled this data set very carefully. Unfortunately, they did not map to the public version that we had access to. This data set is not easily shareable. If you think about it, when you're labeling, this creates inherent biases that are difficult to account for. So you can imagine this could bias your method in a very favorable way or an unfavorable way. And labeling, I think, is a research direction in its own right. And I think Jared linked to some very important papers in this aspect where the labeling was actually the main point of the research direction. In terms of comparisons, this was thought about very carefully. I think it's important not to compare apples with oranges. So for example, in our method here, we're assuming categorical variables. So in terms of comparing something with our method to Foligi-Santer or Sedinle or Stort's 2015, these are all utilizing strings, so they wouldn't be very comparable. There's also a lot of fine tuning going into these particular methods. So if I have done the comparisons, but I think I can show at the very end that they're not really comparable in terms of this, if Jared wants to get into that kind of discussion. And then finally, for computational considerations, I really appreciated the comments by Zhu and colleagues. The Bayesian record linkage problems are slow to mix in general, all of them, especially when the number of duplicates is very, very, very small. And so we thought this sparked important areas of research regarding convergence diagnostics by Zhu and colleagues, as well as better proposals that could allow the Gibbs sampler to converge more quickly. And this was illustrated by Zhu and colleagues on their GitHub webpage. And one thought is maybe some of the tools proposed by this discussion could be used as future convergence diagnostics in record linkage settings. So this is the kind of end of our rejoiner, just to keep things quite short. There were many other thoughtful comments made by all of the discussants. And so maybe it's a good time to open it up for discussion.
Yes, thank you, Rebecca. I would like also to thank the other discussants. Again, both the invited and contributed discussants. One feature of the Bayesian community is to have lively discussion, and definitely this webinar and this discussion has set a good example. So I would like to leave the opportunity to everybody to all the attendees to ask further questions. If you want, you can also raise your hand, and I can allow any attendee to talk and ask the question directly. And of course, the discussants can also ask further questions in case. Let's see. Okay, it looks like we don't have any further question, I believe. I'll wait 1 second more. Any further comments from the discussants?
Yeah, I had a small one on the rejoinder, if there aren't any questions from the audience.
Go ahead.
Becca, would you mind sharing your slides again?
Oh yeah, sure, just a second. Let me find them.
Okay.
Yeah, was there a slide number?
Yeah, slide 6.
Yeah.
Yeah. So this is a really good point, I think. So just a couple of things here. So I think if we're talking about the priors on the linkage structure or co-reference matrix, I think like the Sedinle 1417 prior, the beta bipartite prior, is sort of by default uniform on the number of records in common, and then conditional on that uniform on the linkage structure, which is actually very different than uniform on the linkage structure or co-reference matrix, and better. But you're right, those priors are consequential. I think the point that I was sort of trying to make in my discussion was that those priors are consequential. And in most of these other approaches, you have some knobs that you can kind of vary, right? You can replace that uniform prior on the number of matches with some other prior on the number of matches and do a sensitivity analysis. Where I think that you start running into some potential for trouble is when you bolt on the population size model. All of a sudden, the assumptions about random sampling from larger populations that you make in the population size model are actually dictating the prior distribution over the linkage structure. So that's kind of the distinction I would make between models that are just for record linkage or record linkage and deduplication versus models that are trying to do all three at the same time. Assumptions that we have to make to do population size modeling that are almost incidental to assumptions that we would make in record linkage all of a sudden become very consequential through that link. But sort of the broader point that we're putting prior distributions on big discrete structures, and they sort of almost have to be informative on some aspect of that kind of by definition. That's a really good point and good to emphasize here.
Oh yeah, so if I could just, I think that's a really good point you made. If you don't mind if I'd like to respond. So if I understand correctly, so I do understand the prior on Sidinley for, and Mauricio can certainly jump in because it's his paper. The prior on Sidinley is definitely quite different, but what I looked at in 2016 is how influential those uniform, and I'm using uniform with quotations, how influential those types of uniform priors are when you tweak different things. And they're influential in very different ways. So that's all that I was trying to point out here, is that these uniform types of priors just in a record linkage setting are quite different. And then if I turn to your second point, which is very important, there's two kinds of things that, so you asked we couldn't cover all of the things that you pointed out in your discussion in the rejoiner talk, but we did actually discuss kind of what you asked for regarding the possible consequence due to lack of robustness with respect to the sampling assumptions and the joint record linkage and the post-linkage inference. And so there's kind of two things that you could talk about. So in one paper that we wrote a few years ago in 2018, we investigated how to make inference on the regression coefficients of a linear relation estimated with a response in the covariate. So if you think about this, this is doing something kind of similar, but also different. So it's coming from the different files calibrated on the linked records. And we showed how the linkage uncertainty can be introduced in this inferential process. So on the other hand, we also investigated how the information coming from the regression analysis can modify our posterior on the cluster structure. So this feedback effect, right, it may or not be welcome according to the application. And when the regression model isn't a good choice, this feedback effect can increase the noise or worsen the linkage process. Now, the goal of our paper here is different. So we're arguing that in presence of the record linkage task, our proposed model is to be able to provide a valid statistical information on N. So meaning that we're able to provide an integrated likelihood function for N, which combined with a suitable prior on N, which will produce a posterior that's summarizing what the data can tell about the population size without explicitly designing a statistical model for N. So if you take this argument further, right, you could use our posterior on N as the prior for a better design capture-recapture experiment. So I don't know if that answers your second question. You could certainly do more complex things here, but that was our goal.
Yeah, no, I mean, those are all really good points. I think the last bullet on the last slide that you showed us, the one about model specification, that regression context, you know, I mean, there is an analog here, right? Like you're integrating that, when you integrate that likelihood to get to this marginal for N, like you're integrating against something, right? There's a model for the population size that's under there. And I think, you know, I didn't talk too much about the particular form of that. I'm not really an expert in population size modeling, but I think Mauricio had some very particular thoughts about that as well. So like there is a model living under there. And your last point here, that when that model for the downstream task is either misspecified or maybe just not ideally chosen, that can sort of propagate back to make the record linkage do worse. And that's going to kind of propagate forward again and make the inference in the regression model a little bit worse. And that's something that we can't even necessarily diagnose. The whole enterprise makes me a little bit nervous, but maybe I'm just a fraidy cat.
Okay.
May I jump in?
Go ahead, Mauricio.
Do we have time? Okay.
Yes, a few minutes or more. It's already over 2 hours, so it was supposed to be 1
Okay.
hour and a half, but okay, perfect.
Okay. Yeah, just first one comment about the priors. I think that this is something, I would not say that one of these approaches is better than another necessarily. I think it's just very kind of open-ended right now, because I mean, you can imagine that you could have arguments for being, or for trying to be non-informative, or let's say flat on one characteristic, but then thereby inducing very strong information on some other characteristic of whatever it is that you're trying to estimate. For example, if you try to be flat on the space of partitions, that was what I did in the study in the 2016 paper, the 2014 paper. That's the analysis of applied statistics one. The thinking there was, well, what you really want to estimate is a partition of the file that you want to deduplicate. So therefore, like, why not be flat on that space where your parameter of interest lives, right? Of course, that induces, as like I showed, that induces very strong information on the number of elements of that partition, that is the number of individuals in the data file. Someone else might argue, well, what I want is to be flat on the number of individuals in the data file, but therefore that induces a different structure on the space of partitions, right? So I think that's something that is interesting, and I don't know that I have a final answer to that. I mean, all I can say is that you can evaluate the frequentist performance of these procedures, right? Like, you can run a simulation study where you generate different pairs or different sets of data files with different types of errors. You simply choose the default, different default priors on these spaces, and you see at the end which approach leads to better frequentist performance in terms of precision and recall for the linkage and the duplication of these data files. That would be something that I would be happy with. That would be kind of very compelling. But I would say that it's not necessarily. I wouldn't say that any. My answer to this question, why we ask why these particular models should be considered less dangerous than ours. I would not say that they are less dangerous. So yeah. So there's still a lot to figure out. Now, the other thing that I wanted to say regarding the feedback between the model for analysis and the model for record linkage, what I have seen based on some preliminary studies that I have been doing is that you can, the specification of the model for analysis can have a really strong impact on the record linkage, and it might not necessarily be something that you want. For example, if it turns out that really y, it says that your final analysis is a regression of y on x, and let's say that in reality y is not related to x, right? So that's a particular case of linear regression, right? One where simply the slope is 0. Now you can specify that. You can specify a joint model for record linkage and regression where you specify simply a linear regression. Then you would think, well, if I am assuming that in reality there's no relationship between y and x, and so in particular that corresponds to a linear model. Well, I should be able to estimate that slope using my joint model for record linkage and duplicate detection. It turns out, based on what I have found, when you run that joint model, the likelihood leads to a configuration of the linkage that increases the relationship between y and x as much as possible. So it kind of, by you saying that you want to specify a linear relationship between y and x. Somehow, when you put all of that together, your posterior leads to very strong relationships between y and x. Kind of leads to configurations of the linkage that leads to very strong relationships between y and x. This is something preliminary that I shared in the some preliminary results that I shared in the Latin American Conference of Bayesian Statistics. That makes me really worried about these joint approaches, because that means that this, whatever model you put for the analysis will have a very strong impact on the linkage quality, but that's, you don't know what the true relationship is. That's precisely what you want to discover. So, these joint approaches make me really worried about, what is it that you're getting out of them? Even though they seem appealing, I am worried, the same as Jared. I think I am worried. We need to be really careful about what we get out of these approaches. That's what I wanted to say for now.
Thank you, Mauricio. So one of the goals of a discussion paper is, of course, to provide a perspective on an important field of analysis. So I think that this discussion has been clearly a success in that respect. I think that people that will be able to watch the YouTube video later on will be able to have a good idea of the major contributions in this field, the contribution of this paper, and possible directions for the future. So I see that there was a question that was asked by one of the attendees. I would ask quickly Brunero to answer the question, mostly because we have a YouTube video that is going to stay up, and so people may have the same question. So you previously mentioned that the objective base was not plausible for specifying the prior probabilities for error. Can you expand on that?
Or just simply answer that the model is, as noticed by some of the discussants, is overly parameterized, and in some specific situation, models are at the boundary of identifiability. So in this situation, it's very hard to find a specific values of the hyperparameters that makes the analysis reliable in a sense. And this is a different, I may answer in a different way by saying that in a way or in another, you have to put some prior information into the model, because the data by themselves are not able to tell everything you need, especially when, as in this case, we want to estimate the regular linkage error and the population size.
Perfect. Thank you so much. Thank you again to Brunero, to Andrea and Rebecca for their paper. Thank you to Mauricio and Jared for a very well-conducted discussion and provocative. I think, again, that our readership, our readers will be able to get a lot from this paper. So thank you, and I'll just point you to the end to the bulletin of ISBA, where you can see many further announcements about what's going on in Bayesian analysis. So just have a read. Thank you again. Have a great night, or have a great day for whoever is connected.
Thank you, Michele.
Thanks. Thanks a lot.
Bye.
Bye.
Bye,
Bye, Maurizio. Bye, Jared.
Ciao, Rebecca. Ciao, Maurizio.
Ciao, Brunero. Ciao, Andrea.
Bye-bye. Thanks to all.
Bye-bye. Ciao.